One of the first things we're going to talk about this week is solar radiation and terrestrial radiation. We need to understand where the source of energy is coming from for the atmosphere before we can really talk about the atmosphere. What makes it move? What makes it be what we experience in weather? So all energy on Earth for the sun, for the atmosphere, pretty much comes from the sun, the solar radiation. So think about radiation. We talk about microwaves heating up an oven. Well, the sun, or food, the sun does the same kind of thing to the Earth. It is sending radiation our way all the time, and that is what's heating the Earth. So thinking about that a second here, let's see if we can go on. So what is this flow of energy into Earth, and how the heck does it make our Earth stable and habitable? So electromagnetic radiation is a wave of energy, literally flowing through the air, flowing through things. When you look at a light bulb, you see electromagnetic radiation. When you look at another person, you're seeing electromagnetic radiation. That's how you're seeing them, because we all generate some, believe it or not. So you need to know a few things about this. First off, what is a wavelength? Well, it's the distance between two crests of the wave. If you were out in the ocean, and I like to go out to body surf or take a boogie board out to the wave sometimes, and you'll go up one wave, go down between that wave into the trough, and then back up on the next wave. The length between those two is your wavelength. How frequently those crests occur is called wave frequency. So if they're coming, some days you can just look out at the ocean and it looks angry because the waves are coming one right after the other. That's a high frequency. Now, interestingly, electromagnetic radiation moves at the same speed. It moves at the speed of light. So that means the more frequency, the higher the frequency waves, the more of them there are, the more power, the energy they have. So everything pretty much can be approximated like a black body. What does it mean? All radiation is absorbed and then re-emitted. So a black body would maintain a constant temperature if that happens. And most objects can be approximated that way. It simplifies the math, shall we say. So the wavelength of most intense radiation emitted by a black body is inversely proportional to its absolute temperature. So both the sun, the earth are black bodies. Sun's a whole lot hotter, so the wavelength is a whole lot more intense. For example, you can see here that most of the wavelengths are in the visible spectrum from the sun, or ultraviolet. Infrared is where we exist in our Earth. And here is an interesting thing, that the energy of a wave radiation is actually temperature to the fourth power. So think about it. Earth temperature, we'll say, is 60-some degrees. The sun, 1,000,000. Now you just did that to the fourth power. Tremendous amount more radiation is coming from the sun than from the earth. And as you move out, away from the sun, the further out you get, less and less radiation gets to you. So that's the inverse square law. In other words, if the distance from the sun is the same as the earth, it's 1/1 squared, or energy E equals approximately 1. But say you were out twice as far as this says, then you would get double, 1/4 the amount of radiation. If you were out 4 times as far, you would get 1/16 the radiation. So you can see you're losing the amount of radiation very quickly as you move away from the sun. Here's one of the harder things for people to grasp, I found. So, the sun strikes the earth directly over the equator when it's an equinox. In other words, there's equal sun, March 21st, September 21st are equinoxes. The sun is directly overhead at the equator at that moment in time. So think about it. If you hold the flashlight like this is demonstrating, it would look straight down, very intense beam over that small area. Now, we don't live at the equator. So our sun angle is actually covered a larger angle. And the further and further away you get from the equator, the more that angle increases till you wind up maybe at the poles with almost no sun certain times of the year. So that means the same amount of radiation that hit the equator is now spread over a much larger area. That's why there's a difference in temperature between what temperature is around the equator and the temperature where we are at the poles, because of this radiation difference. And here you can actually see the different angles and all that strike the earth. So, as the poles tilt back and forth, it makes a tremendous amount of difference on the amount of radiation. And, for example, Antarctica, and when it's their summertime, which is around December, January, notice they have pretty strong amount of solar radiation. However, in the middle of their winter, they got none. Singapore, on the other hand, which is very close to the equator, has very little change. It fluctuates as the sun's going around it. And up on Long Island, where Brockport, New York is located, you can see the curve. And that is very typical of what our curve looks like here as well. Here is just the reason why you see the tilt. The Earth never changes its tilt. It's just where it rotated around the sun. So where it's tilted away in the wintertime, for us, our winter, it's then tilted towards the sun in the summertime, when the Earth is rotated all the way around to the other side. Now, the atmosphere doesn't let all solar radiation in. It absorbs some, it scatters some or reflects it, and some is actually absorbed by the Earth's surface. But the total amount has to be accounted for all that solar radiation. So what do we mean by scattering? Well, you ever been outside on a cloudy, dreary day? Well, the top of those clouds are scattering the sun's radiation. They're allowing some back down. That's how you see. But at the same token, a lot of that solar radiation is getting dispersed back. So that's why it might be cooler when you have a lot of clouds around than if you had no clouds that day. And that is what is called reflection also occurs. Think about it when you're outside after a fresh snowpack. Walk outside and you need sunglasses on if there's bright sunshine. The reason for that is snow is highly reflective. It has a very high albedo. Albedo is basically the amount of reflection something has of radiation. So a mirror would be extremely high albedo. So you have the same kind of thing with bright white snow. Or clouds can have a high albedo as well. Now, absorption is when some of this energy is absorbed. Ultraviolet radiation gets absorbed basically in the stratosphere. If it didn't, we would get really sick. We don't like, believe it or not, the human body does not like ultraviolet radiation. It can cause cancer, it can cause other illnesses. That's why the ozone, which breaks up in chemical reactions from ultraviolet radiation, absorbs it as well and protects us from it. Here you can see a satellite picture in the wintertime. You can see the ice and snow there. So where the snow was, there's more solar radiation being reflected. What you are looking at on a satellite image is always the reflection from Earth. So the brighter the image parts, we're probably having things like snow cover or clouds. The darker, water, Earth. Here is actual table that shows you where it's all gone. 47% is absorbed in the Earth's surface. 23% absorbed by the atmosphere. The rest of it, hey, we send it back out to space. We didn't need it in the first place. And because of that, the Earth's principal recipient of that energy, the bottom part of the atmosphere, is the warmest. Other factors take into account what happens further up in the atmosphere then. And there's an equilibrium. Believe it or not, the Earth's temperature on a whole, yeah, it's changing some, but it on a whole is not changing significantly enough to prove there's an unbalance here. If there was an unbalance in the amount of radiation going in and the amount of radiation going out, the temperature would change. Either less radiation coming in and more going out, we get much cooler. The opposite would occur. Greenhouse effect is what stores this radiation down closer to the ground. It's why we're a little bit warmer at the Earth's surface. If we didn't have greenhouse gases, it would be an ice age all the time. And even cold, really, really cold. Hard to live if at all possible. So that is a good thing for greenhouse gases. However, too much of a good thing is not always what you want, as we've all learned. So, Earth emits infrared radiation. We told longer waves. These greenhouse gases grab those longer waves of radiation, absorb it, and then re-emit it. They re-emit some back to Earth. They re-emit some back out into space. The part that comes back to Earth is more radiation coming back to Earth, more energy. It helps it warm up the Earth. The principal greenhouse gas is water vapor. So the more water vapor you have in the atmosphere, the more greenhouse gas you have, the warmer it's going to be. Carbon dioxide is the next one, then ozone, and then methane. So take example on why greenhouse gases, water vapor is so important. If you lived down on the Gulf Coast, are you in a very humid atmosphere there? Let's go to the Southwest, same thing, not a humid atmosphere at all, very dry desert. So at night, in the Gulf Coast area in the Southeast, I lived at Florida State for a while, I can tell you temperatures don't cool at night very much. And that is because of the greenhouse gases, the amount of water you have in the air. Now, out over the desert, you don't have much water. So what happens? It gets much, much colder at night. That's how you know that the influence of the water vapor is so significant on our climate. And this is just the calendar effect where we can show with the healing curve and all, the more CO2, the more temperature rise there's been with time. And yes, the curve is increasing for both here in the last several years. Now, that doesn't mean, that's just part of, we can discuss global warming ad infinitum, and you get all kinds of opinions about it. Most reputable scientists now believe there is some. How much? That's another matter. But I can tell you for a fact that when they do surveys now of scientists, 95 to 98% of all meteorologists, atmospheric scientists believe there's some global warming. It's the magnitude that is in question. I wanted to show you, using a satellite, how we can look at the infrared coming from Earth. So we have typical geocolor, which is basically a visible satellite image. The best. All infrared radiation, if you were up into space at this time and looking down, that is what you would see. Now, infrared does come in different things. So we have a dust curve. Literally, there is an infrared radiation that will pick up dust. that kind of corresponds to dust, reflection of radiation. So when it was so smoky in the east, I wanted to look at this curve, and I could actually look at it and see the smoke coming in and where it was coming from. And there are different infrared bands, and you can see them all listed here: 0.47 microns, 1.3 different meanings. Some are looking at clouds, looking at snow, maybe looking at water vapor at different levels in the atmosphere. Infrared, pure long wave radiation, infrared, is a great one to look at the cloud tops, for example, and see how cold they are. So this is a way of just seeing the impact of how infrared radiation works and how different wavelengths depict different parts of the atmosphere. So it's a very complex system, as you can see.